morning to all. This is Dr. Padma, Assistant Professor, Department of Physics, Institute of Aeronautical Engineering. Today's topic is Junction Field Effect Transistor, simply called as the JFET. So, we will discuss about the introduction of JFET, JFET concepts, basic PN, junction field effect transistor operation, basic MESFET operation. The junction field effect transistor introduction. So, the junction field effect transistor, simply called as the JFET, it is a separate class of the field effect transistors. So, the junction field effect transistor, simply called as the JFET, so it is a separate class of the field effect transistors. So, there are two general categories of JFETs. So, the first is the PN junction JFET, so which is called as the PN JFET, and the second is the metal semiconductor field effect transistor, which is simply called as the MESFET. So, there are two types of JFETs are available. First one is the PN junction field effect transistor, which is called as the PN JFET, and the second one is the metal semiconductor field effect transistor, which is simply called as the MESFET. So, the PN JFET is fabricated with a PN junction, and the MESFET is fabricated with a Schottky barrier rectifying junction, that is called metal semiconductor. So, this is metal, this is semiconductor. So, the metal semiconductor contact is simply called as the Schottky barrier. So, that type of FET is known as the MESFET. So, the junction field effect transistor simply called as the JFET. So, here two general categories of JFETs are available. First one is the PN junction field effect transistor, which is called as the PN JFET. Second one is the metal semiconductor field effect transistor, which is simply called as the MESFET. So, the PN JFET is fabricated with a PN junction, and the MESFET is fabricated with a Schottky rectifying junction. So, JFET concept. So, the concept of the field effect phenomena was the basis of the first proposed solid state transistor. So, the patents are filed in 1920s and 1930s and investigated the first transistor as shown in the figure 1. So, figure 1 is the idealization of the first transistor. So, this is the semiconductor, this is aluminum. So, here the metal contact is there, this is the base. So, the concept of the field effect phenomena was the first basis for the first proposed solid state transistor. So, the patents are filed in 1920s and 1930s. The first investigated JFET is shown in the figure. JFET concept. So, a voltage is applied to the metal plate. So, this is the metal plate. So, when a voltage is applied to the metal plate, modulated the conductance of the semiconductor, under the metal controlled the current between the ohmic contact. So, a voltage is applied to the metal plate, so which is modulated the conductance of the semiconductor under the metal and controlled the current between the ohmic contact. So, good semiconductor materials and processing technology were not available at that time. So, the device was not seriously considered again until the 1950s. So, the good semiconductor materials are not available at that time. So, the device was not seriously considered up to 1950s. So, a voltage is applied to the metal plate, modulated the conductance of the semiconductor under the metal and control the current between the ohmic contacts. So, the phenomena of modulating the conductance of semiconductor by applying an electric field which is perpendicular to the surface of the semiconductor is called as the field effect. So, the phenomena of modulating the conductance. So, conductance is G. So, the phenomena of modulating the conductance of a semiconductor by applying an electric field E which is perpendicular to the surface of the semiconductor. So, which is perpendicular to the surface of the semiconductor, that effect is known as the field effect. So, this type of transistor has also been called as the unipolar transistor to emphasize that only one type of carrier. So, it allows only one type of carrier, that is the majority carrier is involved in the operation. So, the phenomena of modulating the conductance of a semiconductor by applying an electric field which is perpendicular to the surface of the semiconductor is known as the field effect. So this type of transistor is being called as the unipolar transistor. Unipolar means one. So it can allows only one type of carrier, that is the majority carrier. So that is involved in the operation. So basic PN JFET, PN junction field effect transistor, simply called as the PN JFET. So the basic PN JFET operation. So the first type of field effect transistor is the PN junction field effect transistor or PN JFET. So a simplified cross section of the symmetrical device is shown in the figure 2. So figure 2 is the cross section of the symmetrical N channel PN junction FET. This is the N channel PN junction FET, PN JFET. This is the N channel PN junction FET. This is the source. This one is the gate and drain. So here ID is the drain current. VDS is the drain source voltage. VGS is the gate source voltage. Gate source voltage. This is the N-type device. P plus. So these are the electrons. So electrons are the unipolar charge carriers. So this is the simplified cross section of the cross section diagram of the symmetrical N channel JFET, PN junction JFET. So the end region between the two P regions is known as the channel. So the end region between the two channels. So the end region between the two P regions is known as the N channel, and is in this N channel device, majority carriers are the electrons flow between the source and the drain. So in this, the end region between the two P regions is known as the channel, and this N channel device, the majority charge carriers are the electrons. So electrons flow between the source and drain terminals. So the source is the terminal from which carriers enter the channel from the external circuit. The drain is the terminal where carriers leave or drained from the device. So and the gate is the control terminal. So the source is the terminal. From the source, the carriers are enter the channel from the external circuit. The drain is the terminal where the carriers are leave or drained from the device, and the gate is the control terminal. So the two gate terminals is shown in the figure. The figure is the cross section of the symmetrical N channel PN junction FET. So the two gate terminals shown in the figure are tied together to form a single gate connection. So since majority carrier electrons are primarily involved in the conduction in this N channel transistor, the JFET is a majority carrier device. Majority carrier means here the majority carriers are the electrons. So this is the cross sectional of the symmetrical N channel PN junction. This is the drain, gate, sources. Here the electrons are the majority charge carriers. So the two gate terminals are tied together to form a single gate connection. Since the majority carriers electrons are primarily involved in the conduction in this N channel transistor, the JFET is the majority carrier devices. So a complementary P channel JFET can also be fabricated, in which P and N regions are reversed from those of the N channel device. So a complementary P channel junction field effect transistor can also be fabricated, in which P and N regions are reversed from the N channel devices. So in P channel, these are reversed. The P and N regions are reversed those from the N channel device. Holes will flow the P-type channel. So in N-type channels, electrons will flow. Electrons are the majority charge carriers. And so in P channel, the holes are the majority charge carriers. So the holes will flow in the P-type channel between the source and the drain, and the source terminal will now be the source of the holes. So it produces the holes from the external circuit. The current direction and voltage polarities in the P channel JFET are the reverse of the N channel device. So in P channel JFET is generally a lower frequency device, and the N channel JFET due to the lower hole mobility. So the P channel JFET is generally a lower frequency device than the N channel JFET due to the lower hole mobility. So the mobility is lower compared to the N channel JFET. So the basic PN JFET operation, figure 3A shows the N channel PN JFET with a 0 volts applied to the gate. So here VGS equal to 0. So gate source voltage is 0. So VGS is 0. Here this is the drain current. So the gate to channel space charge regions in the IV characteristics for 0 gate voltage. So these are the IV characteristics. This is the drain current on the y-axis, drain source voltage on the y-axis. So here the VGS, gate source voltage is 0. So the graph is linear. So the current and varies linearly with the voltage. So figure shows the N channel PN JFET with a 0 volts applied to the gate voltage. So VGS equal to 0. If the source is at the ground potential and if small positive drain voltage is applied. Now we are applying the positive drain voltage. A drain current ID is produced between the source and the drain. So here ID is produced between the source and drain terminals. So the N channel is essentially a resistance. So ID versus VDS characteristics for small VDS values is approximately linear. So if the source is at ground potential and if the small drain voltage is applied, a drain current ID is produced between the source and drain terminals. The N channel is essentially resistance. So ID versus VDS characteristics are small linear values which is approximately linear. So when apply a voltage to the gate of the PN JFET with respect to the source and the drain, we alter the channel conductance. So it varies the channel conductance. So if you apply the voltage to the gate of the PN JFET with respect to the source and the drain, we alter, it can change the channel conductance. So if a negative voltage is applied to the gate of the N channel PN JFET and gate to channel PN junction becomes reverse biased. So here if a negative voltage is applied to the gate of the N channel PN JFET and gate to channel PN junction becomes reverse biased. So the space charge region now widens. So the channel region becomes narrows and the resistance of the N channel increases. So this is the small reverse biased gate voltage. Here VGS equal to minus V1. So this is the reverse biased voltage. Now in reverse bias, generally in reverse bias, the space charge region is width is more compared to the forward bias. So the channel region becomes narrows and the resistance of the N channel increases. So the slope of the ID versus VDS curve, ID versus VDS curves for small VDS, it decreases. This effect is shown in the figure. So here this is the VGS equal to 0. Gate voltage is 0. Here we are applying the reverse bias voltage VGS equal to minus V1. So here the slope of the ID versus VDS is decreases. So if a larger negative voltage is applied, the conduction is shown in the figure. So here we are applying here we are achieving the pinch off voltage. Here VGS equal to minus V2. Here we are increasing the negative gate voltage. Here if you increase the negative gate voltage, then VGS equal to minus V2. Here it is shown like this. So here we are getting the pinch off voltage. So here VGS equal to 0, it is a linear curve. Here the slope is decreases. VGS equal to minus V1. So this one is the VGS equal to minus V2. If you increase the negative gate voltage, the graph is looking like this. So the reverse biased gate to channel space charge region has completely filled with the channel region. So if you increase the reverse bias gate to channel, space charge region has completely filled with the channel region. This condition is known as the pinch off. So the drain current at pinch off is essentially 0. ID equal to 0 at a pinch off current, pinch off voltage. So since the depletion region isolates the source and the drain terminals, so the reverse bias gate to channel space charge region has completely filled the channel region. This condition is known as the pinch off voltage. So the drain current at pinch off is essentially 0 since the depletion region isolates the source and the drain terminals. So the current in the channel is controlled by the gate voltage. So the current in the channel is totally controlled by the gate voltage. The control of the current in one part of the device by a voltage in another part of the device is the basis transistor reaction. So this device is normally on a depletion mode device, which means that the voltage must be applied to the gate terminal to turn the device off. So the current in the channel is controlled by the gate voltage. The control of the current in one part of the device is by voltage, in another part of the device is by the basic transistor action. So this device is normally on the depletion mode, which means that the voltage must be applied to the gate terminal to turn the devices off. So the basic P and JFET operation, now consider the situation in which the gate voltage is held at VGS equal to 0 and the drain voltage changes. So figure 4a shows the replica of the figure 3a for 0 gate voltage and the small drain voltage. So here the figure 4 shows the gate to channel space charge region and the IV characteristics of the 0 gate voltage for a small drain voltage. Here the gate source voltage is equal to 0. Here this is the graph between the drain current ID and VDS. So the graph is looking like this. So this is the ID versus VDS curves as shown in the figure. As the drain voltage increases positive, the gate to channel PN junction becomes reverse biased near the drain terminal so that the space charge region extends further into the channel. So as the drain voltage increases positive, the gate to channel PN junction becomes reverse biased near the drain terminal so that the space charge region extends further into the channel. So the channel is essentially a resistor and the effective channel resistance increases as the space charge region is widened. So the channel is essentially a resistor and the effective channel resistance increases as the space charge region widens. Therefore, the slope of the ID versus VDS characteristics decreases as shown in the figure. Figure 4b shows the small reverse biased gate voltage VGS equal to minus V1. So this one is the VGS equal to 0, VGS equal to minus V1. Here the slope will be decreases as shown in the figure 4b. The effective channel resistance now varies along the channel length. Here the channel length is L. Since the channel current must be constant, the voltage drop through the channel becomes dependent on the position. So the effective channel resistance now varies along the channel length. Since the channel current must be constant, the voltage drop through the channel becomes dependent on positive. So if the drain voltage increases further, the condition is shown in the figure 4c. So here the figure 4c, the slope will be decreases and it grazes the ID and VDS graph. So this is the VGS equal to minus V2. So the gate here we can achieve the pinch off voltage. The channel has been pinched off at the drain terminal. So any further increase in the drain voltage will not cause an increase in the drain current. So the channel has been pinched off at the drain terminal. Any further increase in the drain voltage will not cause any increase in the drain current. So the drain voltage at the pinch off is referred to the VDS saturation. So it is referred to the VDS saturation. For VDS is greater than VDS saturation, that means the drain source voltage increases further the saturation voltage. The transistor is said to be saturation region and the drain current for this ideal case is independent of the VDS. So at first glance we might expect that the drain current to go to 0 when the channel becomes pinch off at the drain terminals. So here VDS is greater than VDS saturation, the transistor is said to be saturation region and the drain current for this ideal case is independent of the drain source voltage. Basic MESFET operation. The second type of the junction field effect transistor is the MESFET. So the gate junction in the PN junction FET is replaced by a Schottky barrier rectifying contact. So here we are using the Schottky barrier because it is a metal semiconductor field effect transistor. That's why here we are using the Schottky barrier rectifying contact. So although MESFETs can be fabricated in silicon, they are usually associated with a gallium arsenide or other compound semiconductor materials. So in simplified cross section of the gallium arsenide MESFET is shown in the figure 5. So a thin epitaxial layer of gallium arsenide is used for the active region. The substrate is a very high resistivity gallium arsenide material referred to as the semi-insulating substrate. This is the cross section of the N-channel MESFET with semi-insulating substrate. This is the ohmic contact. This is the middle one is the rectifying contact. Again, this one is the ohmic contact. So here the source and the drain both are the ohmic contact and gate will be the rectifying contact. So this is the substrate. This is the semi-insulating substrate. So gallium arsenide is intentionally doped with the chromium. So this is the chromium doped gallium arsenide. So it is doped with the chromium which behaves a single acceptor close to the center of the energy band to make it semi-insulating with resistivity as high as the 10 power minus 9 centimeters per centimeter cube. So the advantage of these devices include higher electron mobility, hence small transistor time and faster response time. So here these are having the advantages of the higher electron mobility, smaller transit time and faster response time. So and decrease the parasitic capacitance and a simplified fabrication process resulting from the semi-insulating gallium arsenide substrate. So these are the advantages of the choosing of the gallium arsenide. So here we are using the chromium doped gallium arsenide. So a reverse biased gate to source voltage induces a space charge region under the metal gate, modulates the channel conductance as in the case of the PN JFET. So the space charge region will eventually reach the substrate if the applied negative gate voltage is sufficiently large. This condition again is known as the pinch off voltage. These are the references for the semiconductor devices. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.